Okay, so this is our third procedure. We have two distinct samples now, two separate populations. So to construct a confidence interval to estimate the difference in the means between them, I copied our summary statistics. So this is all the same data that we've had. We've just only been using list 3 of the combined data because that was our one sample confidence interval and test. So now with two separate samples, one of males, one is females, calling those two different things. In the state plan, again, just to identify what's what, a 2-sample T confidence interval to estimate the difference. We have to identify them somewhere. And so if you see the examples in the book, you would have mu1 equals the true mean score of the males, mu2 is the true mean score of the females. I like to just change the subscripts so that they match whatever the context of the problem is, which we can't always do, but it's nice if we can. So our conditions, if we are talking about the random condition, both should come from random samples, which again, we failed using class data, but that's okay. So we're not extending our results to the greater population. We can only apply them to our groups. Independence for 2 samples, and this was something we didn't do the best job of with our proportions in those procedures, but independent, we need to check the 10% for both if sampling without replacement, and check that the 2 samples are reasonably independent from each other. So we want to make sure it's really like a within and between sort of piece for both of those. And so for ours, we really didn't take them as 2 separate samples. I'm going to say we failed again because we didn't conduct 2 separate independent samples, but populations of males and females at our school are more than 10 times the sample sizes. So we reasonably have more than 290 males and 250 females in the school. If we're looking all school, even if we just looked at juniors and seniors, we have more in that particular grade. So where we get busy with our conditions now are the normal or the large sample condition. So neither sample this time is greater than 30. So we are unable to apply the central limit theorem. So we instead need to, if we can, and we can because we have the data, look at a visual to see what's going on. And if we weren't able to, then we would just have to say, proceed with caution, that we were unable to check to see if outliers were present or to check the general shape of it. So I'm going to switch to the calculator and create all of these things in the calculator, and then we'll just put screen captures. Old rules for the AP test. Not sure what the rules are this year. I would think this still applies, but you can't refer to a picture of something and not have it on your paper. So you can't just say, I created a box plot on my calculator and didn't see outliers. You have to show a sketch of it. Not as nice as the sketches we would have made in chapter 1 with everything neatly labeled, but just a quick sketch, a rough scale to show that you actually created it. Just more evidence that you went through the process of checking it than anything else. Okay, so on the calculator, I still have everything entered into list 1 and list 2. So first, box plots to check for outliers. So outliers and skewness are the 2 that we're most interested in. The box plot is the easiest way to check. It does that 1.5 IQR rule for us. So checking this for the males, and then just zoom 9 to see what the picture looks like. Looks very nice, very symmetric. You could trace at this point to get your 5-number summary so that, like I said, you could easily just sketch it onto your paper. And then we can switch over to a histogram to check to see if it even shows a bell curve. So if it's roughly a bell curve, then that again is leaning us towards showing that it's approximately normal. So this one looks really good too. Same thing, you could trace or you could clean up this window a little bit because again, with the histograms, when you go to the window, it doesn't usually count by a scale that we would like. This one actually worked out. It went from 3 to 10 counting by 1. Usually it's some crazy decimal point for the scale that's not realistic. The gem that we always seem to forget about is the normal probability plot. So this last one will plot all of the values with their corresponding z-scores as a scatter plot, and it indicates normality if this is an approximately linear curve. Zoom 9 again, always easy for Zoom stat. So that, again, because we had a lot of repeat scores, that's why we see the repeats in the values, but roughly linear for this one. So the males check out. Okay, now switching gears to check for female shape. We have to check for all of them. So if we start with the box plot again and look at list 2, go straight to Zoom 9 there. Oh, that's odd. So this is skewed to the left, still not an outlier though. And let me trace and see what happened here. So we have a minimum score of 4, a Q1 of 6, and also a median of 6. So we kind of collapse that left side of our graph. 7.5 and 8. So no outliers to speak of, but obviously something else going on. If I switch it over to a histogram, this should not look like a bell curve. Does not look like a bell curve. Some of those crazy gaps are in there. And again, so here's where it does the goofy thing that it likes to do. So if we change this to 8 and count off by 1s, what does that look like? So I see the left skewness here this time, but I don't see those gaps instead, so not so bad. And then normal probability plot. So while I'm checking all of these, you do not need to check all of them. So if you're most concerned about outliers, which we are in smaller sets of data, the outliers are more an issue of the non-normality because they tend to come with some skewness, whereas just because it's skewed, it doesn't necessarily mean there are outliers. So you don't have to check all of them. You can check some of these plots, sort of like wherever your focus might be. And then sometimes you don't have the data. And so, like I said, if it's just less than 30, we have to recognize that we have to proceed with caution that something else might be going on. So the normal probability plot, just because we had scores of 4, 5, 6, 7, 8, doesn't look terrible. But because there are so few 4s and so many 6s, 7s, and 8s, it appears not quite as linear as what the males were for this one. Okay, so now that the conditions are checked, we can move on to the do step. So we have our estimate, which is the difference in the sample mean. So the mean of the males minus the mean of the females plus or minus our critical value, which is T star, which is somewhere on the table. And then our combined standard error here for males and females. And so S squared of the males over the sample size plus S squared of the females over the sample size of the females. So a lot going on. So we have some of these. We have 5.966 minus 6.44 plus or minus some T star that we don't know. S for the males, I have 1.426 squared for 29 males plus 1.227 squared. 227 is a great show if you're looking for something to watch. Over the 25 females. So we could find T star at this point from the table, plug it in. It would be considered, again, our conservative T star. And we use the smaller degrees of freedom. So the degrees of freedom for males would be 28. And the degrees of freedom for females would be 24, just 1 minus the sample size. So we would go to row 24, which we could actually go to in the table without having to round anything, and get the T star from that one if we wanted to. Or we could say that we are going to finish with the calculator. So under stat test, there is a 2-sample TCI that we can use. And I'll go to the calculator screen and do that. But what you should see is that you have degrees of freedom of 51.9999 and some other crazy decimal points. You do not need to know the formula for that. The textbook shares it with us, but never will you have to calculate those degrees of freedom. It's just knowing what the technology does to piece those together. So here, negative 1.199 and 0.2502. The interval contains 0. So when we look at our hypothesis test in the next lesson, that means we're not going to have enough evidence to reject the null hypothesis, at least not for, this was 95%. Okay, and so again, seeing it by hand versus the calculator, if we go to a test, it should be the 0. Always a little slow. Okay, 2-samp T interval is what we're looking for. We have the data. If we wanted to enter the stats, that would just be like I gave you the summary table at the beginning with mean, standard deviation, and sample size for each one. So list 1, list 2, 1 for the frequencies, it's 95%. We never pool. We would be assuming that the population standard deviations are the same, which is a crazy assumption to make. And so again, that's the interval that I found, the goofy looking degrees of freedom, and confirmation of what all those summary statistics are from the list of data that we had. Okay, so here we are back in the Google Doc just to finish things up. Some notes about how we check normality are 3 different options. I gave all 3 pictures for the males, all 3 pictures for the female data, and then here we have the do step written out. And again, it's not like you have to show the calculator screen, but just to show what that looks like. So finally, our conclusion. We are 95% confident the true difference in mean IQ test scores of males and females, and putting males first because we did males minus females. If you wanted to put the true mean difference and use the notation mu sub f minus, mu sub m minus mu sub f, that would be fine. If you had subtracted them the other way, it would just switch the values and the signs, still contain 0. So we are 95% confident the true mean difference in mean IQ test scores of males and females is captured in the interval from negative 1.199 to 0.2502. You don't have to include this, but like I said, we'll see in the next lesson, because the confidence interval contains 0, there is no significant difference between the 2 mean scores at the 0.05 significance level. I don't know if at 10%, I don't think it's going to shift all that much, but we might just miss 0 with a smaller confidence interval. So that is your 2-sample T confidence interval, which again, bouncing back into 10.2 just to keep the 2-sample stuff together. So we won't have to go through all of those conditions again for our test. They're going to be the same ones.